Hello everyone, welcome to another Python talk that I originally held at a Python Meetup of the SaarPython Meetup group in May 2023. It's titled "If you needed to quack, make sure it's a duck." This is a post recording. I didn't record at the original meetup with the audience, so I could again take a bit more time because I actually found that quite nice last time, and also because I guess I need to train doing live recordings a bit more because it didn't work so well this time again. Anyway, yeah, based on the title you probably can already guess that this is about duck typing in Python, and in particular how to type Python interfaces. Let's dive right in. So, this is me. My name is Sebastian. I like coffee, bouldering, and I like programming in Python. And I work at the company Native AI, who sponsored the meetup this time again. First, before we dive into the actual topic, typing interfaces, we need to talk about duck typing in order to understand what I'm talking about later in the slides. The Python type system is called duck typing because it's inspired by the duck test, which is a philosophical principle which is often paraphrased as: if it looks like a duck, swims like a duck, and it quacks like a duck, then it probably is a duck. I don't actually know who said that. Maybe there is no original author, but probably he or she was a philosopher. So let's keep that in mind. But what does that actually mean? Well, first of all, Python types are dynamic, which means variables can take any value, regardless of the type. We don't need to declare anything up front, and we can change the type of variables on the fly as we like. For example, we can put a number in, and then following that also a list of strings, and so on and so forth. The variables could be viewed, for the scope of this talk, as containers for values regardless of their type. And Python types are, second, only checked at runtime, with an emphasis on only, which means when you assign something to a variable, Python doesn't really care. Only if you try to use the value for something, the type will be relevant. Meaning we can assign a string to my variable here, we can then assign a number, and if we call prime factorize on my variable, assuming that prime factorize actually does a prime factorization of a number, this will probably do something reasonable. And if after that we try and stick a list into the same prime factorize function, this would probably raise a type error or value error or attribute error at runtime. Python would run until this point and actually try its very best to actually execute the prime factorize function, but at some point it would probably realize that you can't, for example, do division with a list, and at that point raise a runtime exception, which is something we usually want to avoid, right? And third, last but not least, Python types are protocol based, and this is a bit more unintuitive. What does it actually mean? Let's take a small example here. This statement here, n times 2. Caveat, this is probably not exactly accurate for all the people that know Python very well, but I think it's accurate enough for the purpose of this talk. When the Python interpreter comes across this statement, it has a look at this statement and says, oh, we have a left operand n, which should be multiplied with the right operand 2. What is actually the type of n? And it looks it up and realizes, okay, it is this certain type, and I've denoted it with a little duck emoji here because we don't know what the caller has put in here. Does duck actually have an attribute $_mul for multiplication? And this is the actual protocol. The operator multiplication is in Python usually implemented as a member of a type, as a function on a type. And if this type does have the multiply, Python will try to call type.multiply on the number n and the 2. So yeah, this is what's meant by protocol based. These protocols are basically behaviors on types. And the duck typing means that whenever you want to do something with an object, the object needs to support the behaviors that you want to achieve with the object. For example, multiplication with another number. In consequence, this means if you invoke double with 21, which is a number, obviously numbers implement multiplication with another number. It will result in a 42 in this case. But surprisingly, maybe to some, you can also invoke double on a string, because strings also happen to implement multiplication with numbers, resulting into a string repetition in this case semantically. Same is true for lists. If we stuck something into the double function that doesn't implement multiplication, for example, let's assume there's a mighty duck class, which may happen to not implement the multiplication with another number, then bad luck. At runtime, this will crash, although it is like valid Python syntactically. It will run just fine until it actually realizes that there is a type error here. So since we don't want these errors to happen in a production system when our code is deployed anywhere, like unexpectedly, how do we make sure that we don't mess this up as programmers? Well, static type checking to our rescue. There is a lovely tool called mypy, which is a static type checker for Python. You can install it via pip or download it. Otherwise, run it on your Python code. It will not execute the code, but it will try to infer the type of every statement and variable you have in your code and see if it finds anything that is odd, that will likely cause a runtime type error once you try to execute it. And mypy can do clever things about type inference, like find out what the type of a statement actually is, but it gets even mightier if you start telling mypy the types of certain things that you would expect in certain situations. And this is where the new Python type annotations, well, I'm saying new, they're not exactly new, but one of the more recent features of Python, they come into play. Consider, for example, this function here, make it quack, which takes an object. And with this colon syntax, we can actually tell the mypy type checker that we expect object to actually be a duck. And with the arrow, we denote that we expect this function to return nothing. Which means when we invoke make it quack on a duck object, then mypy sees, oh, we actually use it correctly. And if we try to call it with a 1, mypy sees, oh, 1 is of type number, is of type int. And this violates our expectation in the function that we want to receive a duck. So mypy will actually output an error. Note though that this is not enforced by the Python interpreter itself. This Python code is totally valid and it will execute up until the point where we try to make the number 1.quack, which obviously doesn't work. So, typing an interface now into the main topic of this talk. Let's say we have this function here, just duck things. It expects to get an object, which I annotated to be hopefully a duck. And then we make this object walk and we make this object swim. And let's say we have Daisy, an instance of duck, and we invoke just duck things with Daisy. This should be totally fine, right? But wait, we also have Perry here. He's not a duck, he's a platypus. We can still stuck Perry into just duck things and it will execute just fine. Because look at this guy. He's not a duck, but sure, he looks like he can walk and swim. He's even a bit similar to a duck optically, I think. But mypy will not be happy about this. Certainly, platypus is not a duck, so we should not use this function with this object, even though this is totally valid Python and it will even execute just fine. So what do? Perry is unhappy about that. Well, we may use typing unions, denoting that, okay, maybe it's fine that object is not necessarily a duck, it could also be a platypus, so like an option of the two. And now Perry is happy again, and even also mypy is happy about that now. But how about a goose, like Gustav here? He'll now be unhappy because he can also walk and swim, but he's still not allowed into this function. So you see where this is getting. We can't really foresee, or we don't really want to foresee every possible object type that we might be able to put into this function, or that we might want to put into this function, that would execute just fine. Like, we can't go ahead and extend this union every time we come across a new class. So inheritance to the rescue. Here we define a base class, we call it duck-like, and we say everything that is duck-like should be able to walk and swim. And in this case we even make it an abstract base class, meaning that everyone who inherits from this class needs to implement these methods themselves, if we do it correctly. So that's nice. Now we can just annotate our interface with we desire object to be a duck-like, and whoever wants to put anything into this function just needs to make sure that they inherit from the duck-like, right? This can scale arbitrarily without the necessity from our side to actually adjust the interface, which is really nice. So we made Gustav happy as well. Well, Perry doesn't really like to be called duck-like, but that's fine. I mean, at least he can use the function now. But, well, what about dogs? For example, a pug, which is a specific dog breed. Should they actually inherit from duck-like? I don't know. This little doggo here seems to be a bit sad about it. Well, that's how it tries to look to the Python interpreter now. Seems a bit weird, like the wrong abstraction actually. So it could get even worse. For example, imagine someone decided in the future that every duck-like should now also be able to quack as well. This is not really relevant for our function itself. It just desires objects to walk and swim. Nevertheless, everyone inheriting from this abstract base class also needs to be able to quack now. And how would our poor doggo implement the quack method? It would always sound like a bark, right? That's not good. Or it could get even worse. Say we don't even have control over our pug class. Maybe we imported it from doglib, so we can't make it inherit the duck-like on our own. We could do some trickery with multi-inheritance, like have a duck-pug class that inherits from both the dog and the duck-like interface thingy. But, well, I've done this in my professional career before and I didn't like it. It's weird. So there is a different option. We can use typing protocols as well. A typing protocol looks a bit similar to the abstract base class you've seen before. We basically define a class, it inherits from typing protocol, and it defines some methods. But if you look closely, our dog breed now doesn't need to inherit from it. It just needs to conform to the protocol. from the perspective of the type checker. So here we basically have implicit subclassing, so to say, or rather we have defined an interface that can implicitly be implemented by any object that we stick into the function, which is really neat. And even if we have a duck now, and the duck starts to be able to quack as well, it doesn't affect the dog at all. Now we even made Doggo happy with our interface. So when should you use what? Well, unions, or in the most simple form, a union with one option, just a simple type. You could use that if you want to be very strict about acceptable inputs. Like it's a very valid design decision if you say, I have this just duck things function and I only want people to use it with actual ducks. I don't care if dogs would theoretically also be able to enter this function. No, I don't want that. This function is meant for ducks. You should not misuse it anyhow else. So if you want that, unions are a good way to go. However, inheritance could be used if you want to do something like you want to use other benefits of inheritance, like you want to provide shared or default behaviors of the things that you put into your function, say database objects. If you have an interface that communicates with the database, then maybe the objects you want to put in or get out, you want to provide serialization behavior with the parent class, and everything that inherits from it should also have these pre-implemented behaviors. Like that's perfect for inheritance, so why not also use the base class as a type annotation and then type check stuff with it? But you still want to allow for arbitrary types to be put into your function without knowing upfront like which types that might be. It makes your interface more independent from the type of stuff you want to do with it later on. When to use protocols? Well, if you can't enforce inheritance nor know all the expected types up front, or you just want basically static duck typing. And if you remember back to the first slides where I explained duck typing, specifically the protocol character of it, then protocols can be understood actually as being able to statically type annotate what the Python interpreter would do on the object, what it expects the object to be able to do, the behaviors it demands from the object, right? So using typing protocols as a type annotation is the closest thing you can achieve right now to actual static duck typing, making mypy check how the interpreter would use the object at runtime as well, which I think is really brilliant and a really nice way to view this method of using it as type annotations. And that's actually it with my talk. And if you have questions, then since you're not part of the original audience, you'll have no other way than putting your questions into the comments or message me on whatever platform I will upload this. Thank you very much, and see you maybe soon for another talk.